Hello, Bang.
Hello,
Hello. Long time no see.
lama tak jumpa kan.
Yes.
How are you? Everything okay?
Yes, everything's fine. Yeah. How are you? You're
Yeah,
in where is it? You came?
UKM.
The city.
Selangor, somewhere near Kuala Lumpur.
Oh. Yeah, yeah,
You know
yeah.
Selangor, right?
Yeah, I know Selangor, but I've
So
never been
basically, it's
there.
in the Bangi. The,
Oh, yeah,
the,
yeah, yeah.
the state is Selangor.
Okay, I familiar with Bangi.
Oh, you been Bangi before?
No, not there, but one of my friend take me somewhere near there.
I see. So it's about 30 to 40 minutes to from KL, I think.
Ah, okay. Oh, nice to see you.
Yeah. How was it
So
in Universitas Erlangga?
yeah, I'm in the Universitas Airlangga. I'm in nanotechnology engineering.
Okay.
Yeah, and yeah, the study program is a recent one. It's established in 2019.
You
So
means the nanotechnology disciplines.
yes,
Uh,
the specific department. So the study in the specific the nanotechnology engineering is established just recently, 2019,
okay, so means that
2019.
you have like undergraduate student in which they have bachelor in engineering, nanotechnology, something like that. Is
Yes.
it?
So
Oh,
the most of the participants today will be the undergraduate student from the nanotechnology engineering.
mm. So for nanotechnology, basically is like you have 4 years subject, right? That one, the course is basically 4 years.
Yes,
Oh.
4 years.
So today one is final year students
No,
or
this one is actually the first year students
oh,
because
okay.
we still only have one batch of
Mm-hmm.
students. So the next intake will be the second batch of the students. So
Also now one is the first batch.
yeah,
Ah,
no one is
okay,
the first batch.
good. So you are
So
teaching the first batch of nanotechnology engineering student, right?
yeah,
Good, good. How much the total the class? So introduction to nanotechnology is basically the compulsory subject, is it?
yeah. Wait.
Okay, okay, good.
So the total student it's around 80 students.
Okay,
Yeah,
so
but
the
right now is the calm before the storm because next week will be the final exam for the semester. So
okay.
yeah, most of the student is not having any class right now.
Hmm. So you are, I mean, because in Malaysia now we are basically we are work from home, right? So
Yeah,
how about in Indonesia?
from Indonesia it's mixed. There we are allowed to work from the office, but only a low number, like a 20% of the total capacity of the building or the department. So not
Also,
all, and the student, every undergraduate student is studying from home, but the final year student that doing research or any master or doctoral degree that doing research are able to do experiment on the lab.
oh, I see. Okay, good, good. Because now basically we undergraduate student we are online learning, so it's like except for the final year lah, but we tends to go to the online one because that's quite serious in Malaysia now, right?
Yeah. And how about have you been getting your vaccine yet?
Yeah, I got it. My
Oh,
first dose last 2 weeks, I think. Last 2 weeks. In the early
oh,
of June. In the early of June.
okay. So in Malaysia, they already started vaccination for people below 50 or 60.
Yes, yes, yes. Already started. Yes, correct.
Oh, that's good. That's good.
How about you? I mean, is it?
Yeah, the vaccination for people below 50 or 60 is maybe started this month or last month.
Mm,
But the people work in the education or like essential position, essential job has been getting it from like last month, last 2 months.
mm.
So I've I've got it in the last 2 months in May, I guess.
Okay, okay. Because we have a different batch lah. Basically, it's frontliner first, right? Then followed by
Yeah.
the oldest one, means the 70 to 80 years old, then 50 to 60. Now I think it's a 50 to 60, the stage, and coming
Ah.
out less than that.
So because in Indonesia, like I don't know about the other region, but in Surabaya, the vaccination rate of the people above 50 or it's already for the first dose is already above 80%. So they started to do for the people below 80, but 80, yeah, I
Mm.
guess. But they
Means
still
the
have,
ones that with the high risk one first, lah, right?
yeah, we aim for the high risk one first, then next we move to the lower risk one.
But hopefully lah, we can get the
Yeah,
vaccination immunity soon,
soon. Yeah,
so that we can
hopefully.
travel around later on.
Yeah,
Like, we just like stay at home, right?
yeah. I've been wanting to go to UTM. Like before, I've talked with Dr. Aisha, and then
Mm.
even before, far before the COVID hit, and I planned to go there, but the COVID hit and everything stopped. Then, okay.
Yeah, please come later on after all this
Yeah.
finish, right?
Yes, I will.
I think
Oh.
everybody should be miss you a lot.
Oh, okay. So the time is already 1:07 in GMT plus the GMT plus 7. So maybe the lecture we will start the lecture. How
All right.
about it? Fine. Is it
Sure,
okay?
sure. Okay, no problem. We can start now.
Okay. Okay.
Um,
Good. Afternoon, everyone. All the students and all the participants. So today we are going to have a lecture from Dr. Tehli Peng about the uh, discovering material for carbon dioxide capture and conversion. So I will read a little bit about Dr. Telipeng. Is it if it's okay with you?
yeah, yeah, sure, sure. Just
Okay. So she is my senior. She is my guide when I'm doing my master, and her doing her PhD. So she is from Malaysia, and right now she is a faculty member of the Department of Chemical Sciences in the University Kebangsaan Malaysia in Selangor, Malaysia. And she got her bachelor degree in chemistry from UTM, and you skip your master degree and you got your PhD degree directly from UTM
yes,
too. So she graduated she got her PhD degree in 2016, and she is a best student with an award at that point. And the research achievement is also amazing. She already published around 32 paper, and most of the research of her is material material development, and then carbon dioxide capture and conversion, renewable energy, and heterogeneous solid acid base catalysis. So that's a little bit introduction for me. If is there anything you want to add, Dr. Tahli Pang?
so later on I just because I have one slides about that. Maybe I can share later on,
Okay.
right?
So
Thanks.
maybe not to drag this further, I'll give the opportunity to start the lecture to you, Dr. Pang. Please.
Thank you. Uh, Thank you, Lutfi. We used to call it Lutfi, right? So now it's become the Dr. Lutfi.
No, no, no. Please call me Lotfi. Yes.
Okay, I will share the slide. So you can see, right? Is it?
Yes, we can see it.
Okay. Hmm. Okay, so a very good afternoon and selamat siang, right? To all the lecturers and students. I am Teh Peng. So usually people call me Dr. Teh or Dr. Peng. I'm from Departments of Chemical Sciences, Faculty of Science and Technology, University Kebangsaan Malaysia, which is located in the Bangi, Selangor. So it's my great pleasure to be here today. I am very delighted to have the opportunity by the Universitas Airlangga, especially faculties of advanced technologies and multidisciplinary to discuss about today's topic, which is material for carbon dioxide captures and conversions. First of all, I would like to outline the main point of my talk today. Let's take a brief look at the agenda of today. So I will begin with some self-introductions, followed by some introduction of my institutions. Then we go to the CO2 emission background. Then we move on to the carbon captures and conversion concepts. We will discuss a little bit about nanotechnology and nanomaterials, and I will be share with you some of my current research in this field. I hope that in the end of this lecture, you will basically have some brief ideas and better understanding of material for CO2 captures and conversions. I will be very pleased if you have any questions to ask. Then I can answer it at the end of these lectures. Okay, let me begin with some of these self-introductions. Okay. As mentioned by Dr. Luffy, I am graduated from the University of Technology Malaysia. So basically, my PhD project is about carbon monoxide methaneations to producing gas using mesoporous ZSM5 catalyst. So I have thanks to both my supervisor, okay, my late Prof. Sugeng Trivayono, and also my co-supervisor, Prof. Dr. Aisha Abdul Jalil, for their guidance throughout the PhD journey. Then after that, I joined the Faculty of Science and Technology, University Kebangsaan Malaysia, at end of the 2016 as a senior lecturer there. Basically, my research expertise will be focused on the advanced material, heterous acid-base catalyst, and renewable energy, and also CO2 capture and utilization. Okay, from this picture, you may see this is my family over here. So this is my previous lab mates and also some of the current one in which we have a conference. Usually the conference time is our gathering time, right? There's some activities in our faculty, and also it's very honored to join the 2020 Southeast Asia International Joint Research Workshop on environmental green technology and also sustainable energy in Taiwan last year, before the COVID-19 pandemic started become very serious. Okay, a little bit about my university, University Kebangsaan Malaysia. So this is the map of the Malaysia. So basically, University Kebangsaan Malaysia or National University of Malaysia is located somewhere here in the Selangor. And it's about 30 to 40 minutes from Kuala Lumpur. And UKM is one of the research university in Malaysia. And we have about total 15 faculties and also 12 institutes, which cover different disciplines and also fields, such as science and technology, social science, we have economics, health sciences, and engineering, and etc. Okay, so this is our beautiful campus, okay, located in the Bangi. We also do have a UKM Global, in which is the International Relations Center for strategic collaboration and global networks. So I got attached a link over here about UCAM corporate video. You may watch it if you are interested to know more about UCAM. If somehow, because I get to know from Dr. Luffy that today student mostly is undergraduate. Maybe in the future you can pursue your postgraduate study in UCAM, right? Okay, let's start today's lectures, a little bit of the introductions. So I would like to share with you some interesting facts about greenhouse effect. I think everyone should have heard about or get a little bit familiar with the terms of greenhouse effect, right? So basically, sunlight passes through the atmosphere and warm the earth. Then it will be emits the infrared radiations is given off the earth. Most of them will be escaped through the outer space, which allowing the earth to cool. But there is some infrared radiation is trapped by gases in the air, in which we call it the greenhouse gases, for example, like carbon dioxide. Okay, keeping the earth warm and enough to sustain life. This is called the natural greenhouse effect. And usually this occurs naturally without any human emissions. But somehow now we are more concerned about the one that call it enhanced greenhouse effect. This effect is referred to the increasing of the heating of the earth and resulting of higher amount of the greenhouse gases being trapped and released into the atmosphere from human activities. So increasing level of CO2, so it will be increasing the amount of the heat retained, in which it causing the atmosphere or our Earth, Mother Earth surface to heat up. That's why we feel getting warm each day, right? So these human input greenhouse gases like CO2, CH4, basically it will affecting the natural balance of our nature, and it will cause the melting of ice in the polar. It will cause rising in the sea level and causing the flood. It will have global warming and also climate change, which cause the crowd and also air pollutions. This slide shows you the difference between the natural greenhouse effects and also the human enhanced greenhouse effect. So you may see here that naturally we have a little bit of very low amount of the CO2, okay, to warm our Mother Earth. But if we're getting more greenhouse gases, it will be getting serious. And this will cause climate change and global warming. Back in 2018, there is 80% of these greenhouse gas emissions is carbon dioxide. Then 10% is methane, 7% is nitrous oxide, and 3% is from the fluorinated gases. From here, we can conclude that CO2 is the major contributor to climate change and global warming. On the right side here, I show you some of these tables on the characteristic of the greenhouse gases. Greenhouse gases basically are released from the combustions from the fossil fuel, burning of the fossil fuel, deforestation, and some of the fermentation process. However, this gas basically can remove by the natural photosynthesis process and also photolysis in the stratosphere. If too much of this infrared radiation is absorbed by the greenhouse gases, then they will contribute to a very serious problem, which is global warming. Urban developments basically is the one we acknowledge as a contributor to the greenhouse gas emissions. Usually in city, like Surabaya is also a city, right? So it consumes energies, and this city also center where the environmental degradation and effect of temperature rise and can be more, we felt the most. From this figure, we can see that Indonesia, because transportation sector in Indonesia emitted the highest amount of the CO2. It's about 138 million tons, followed by Malaysia, then Thailand, followed by the Philippines. Thus, a very low carbon mobility solution basically is needed to minimize the CO2 emission. I have shown you here, for example, we have a car. So a car using a petrol, right? So it can generate about 0.162 kilogram of CO2 per km. If you are using the natural gas vehicle, it can generate lower CO2 emission. It's about 0.130 kilogram of carbon dioxide per kilogram. This has leads us to the next point, which is Malaysia has made a commitment to reduce the carbon emissions, in which 45% reductions as compared to the 2005 level by 2030. While the Indonesia, one of the world's biggest greenhouse gas emitters, also put forward a plan to achieve a net zero emission by 2070. Here is some of the example of the existing policy on the environmental sustainability. Many countries, okay, not limited to this that I shown here, adopted the implementations of the low carbon city to achieve a very sustainable development. So for example, Indonesia have the low carbon city planning project in Surabaya, Indonesia. Japan have a Japan action towards the creation of low carbon city. Korea have Korea strategy for low carbon green city. And Malaysia also have a low carbon city framework. This is related to what I was saying earlier. In low carbon city framework of Malaysia, there are several CO2 intensity reduction strategy in various sectors like energy, transport, waste, land use change, and forestry and agriculture. But I didn't want to go detail on this. Okay, the next topic I will be focused on these what we call CO2 captures and conversions. So CO2 captures and conversion is one of the alternatives to mitigate the anthropogenic CO2 emissions. So the current CO2 readings updated by 20 June 2021 is about 419.18 ppm, which is increased about 2.6 ppm as compared to last year, June 2020. I would like to draw your attention in which in a pre-industrial level, basically is about 270 ppm. But now it's already increased to above 400 ppm. In this case, it is important to capture the CO2 as well as converting it to a various value-added products like dimethyl ether, hydrocarbon, methane, hydrogens, formic acid, and methanol. Converting the CO2 into value-added products is very significant and also a very energy-demanding process. So by overcome this energy barrier, basically we need a material or we need a catalyst. So catalyst plays a crucial role over here to reduce the energy barriers for these reactions. Nanomaterials in particular can be used and designed and also optimized to enhance the energy efficiency and also selectivity of CO2 conversion as well as for CO2 capturing. For today's lecture, I will be focusing on only chemical conversion, especially in only methane and also the hydrogens productions. Now I would like to turn to explain the existing CO2 capturing process. We have three types basic techniques used to capture the CO2. One, we call it the post-combustions. Then we have the pre-combustions. Then we also have these oxy-fused combustions. For post-combustion, it's the techniques, decarbonization techniques based on the CO2 separations after the fuels combustions. While for the pre-combustion CO2 capture processes is to reduce the CO2 contents from the fuels before entering the combustion state. So it reduces over here before it entering the combustion state. Next, if for this oxy-fuel combustions is the main purpose. The main purpose is basically to remove the inner gases from the combustions of the fuels gases. Okay, sorry. By comparison of these three existing CO2 capture process, the pre-combustion basically is relatively easy and widely employed approach, whilst the post-combustions can be used and efficiently to be used at the lower stream of CO2. Let me elaborate further on the CO2 capture technology. Okay, if in the post-combustion, we have three types. We have absorptions, and also membranes. So from the three techniques that I mentioned earlier, I would like to highlight that post-combustions is basically a feasible applications because we can reprofit it into the existing power plant without much modifications of the existing plant. So you may see this, the process of these adoptions is compared to the AB and AD. Usually in AB, people are using the amine crabbing or amine-based solution. So it will cause products several drawbacks like solvent degradation, corrosion problems to the machines, to the instruments. So people are getting to more focus on the absorption, the AD. But the AD here, we need to develop newer absorbents, or we can say a highly active and also stable absorbents. And the absorption, the AD here, basically is have a reduced energy consumptions. It can be more easy to handling, and also it will be solve the corrosion problem in the absorptions by using the amine-based solutions. To expand a little bit on these, as demonstrate the comparison of different post-combustion CO2 separation techniques. So we know that the established technology is the AB, the absorptions. But the absorption can be appear to be a much better candidate for CO2 captures. Okay, it may be due to the less capture limitation, such as if you are using a durable absorbent, so we have a high absorption capacity, then it will be more economical, low regeneration energy, easily handling and recovery, and also will be high uptake efficiency under humid condition. If we are talking about absorption, basically we are focusing on the CO2 absorbent. But various absorbents have been applied in this CO2 capturing process. I would like to emphasize that each absorbent will possesses their own unique characteristic and also their own limitation during their application in CO2 absorption. For example, we have a metal oxide here, in which metal oxide have a high availability, then it will be low toxic and also low cost, as well as it will have absorption ability over a wide range of the temperatures and also pressure condition. We have also silica material, silica-based absorbents. It is the high surface areas, tunable porous structures, and good thermal and mechanical strength. Each should be highlights that the high absorptions, the high CO2 absorption performance is related to the absorbent physical chemical properties. And the physical chemical properties basically will be depends on the modification approach that used as well as during the synthesis phase. To summarize, absorbance for the selective captures of CO2 for the gas effluents, it will be needs to meet several specifications. So this slide basically shows the principal criteria for designing an ideal sorbent for CO2 capture. It must have the high absorption and selectivity, high thermochemical and water stability, high kinetic rate of uptakes. We also concerns about the heat of absorption, means the interaction between the absorbent and also the absorbate, the CO2. And it must be cost effectiveness and high recyclability. I would like to turn in your attention to the CO2 conversion. CO2 conversion basically is mostly is a non-spontaneous reaction, and it needs a very high activation energy. So CO2 conversion reaction, it requires a very suitable catalyst. So this catalyst, it can lower down the activation energy, and it allows the reaction to happen and even accelerate the kinetic of the reaction. Nanomaterials is one of the material that can speed up the chemical reaction due to the ultra high surface area, and these are we refer to, we call it nano catalysis. As I mentioned earlier, one of the value-added products of CO2 is methane. So methane is also one of the most efficient means of energy storage. So you may see over here in this figure, is presented to you that the methane have a higher recoverable energy density as compared to other candidates, right? So there is a two conventional methane synthesis method. One we call it the Fischer-Tropsch process, another is Sabatier reactions. Both process is the viable options to synthesize methane. And down here, I show you the reaction of Sabatier reactions. Sabatier reactions, we can call it this CO2 methanation. It uses the CO2 react with the hydrogens to produce methane and also the H2O. Another one is the Fischer-Tropsch reactions. Basically, is to produce the hydrocarbons. And both reactions it will be is highly exothermic. And for the Fischer-Tropsch, it needs a very high pressures. Another CO2 conversion that I would like to introduce to you is the CO2 dry reforming of methane. So in this reaction, it uses both the greenhouse gases, the CO2 and also methane. Okay, so in this table, it shows the main reaction, the dry reforming of methane. So it uses the methane and also CO2 to produce the syngas, the mixture of the CO and also the H2. And it also have few side reactions like the reverse water gas shift reactions, the composition of the methane, the proportional of the carbon monoxide, and also hydrogenation of CO2 and also the CO. For your information, the DRM or dry reforming of methane is thermodynamically variable above very high temperature. It's about 700 degrees C. So this high temperature reaction, it will promote DRM and inhibit the side reaction. But from the economic and also technical perspective, it will be more beneficial if we can lower down the temperature of the DRM to get it lower than the 700 degrees C. By doing this, we need a very stable, we need a very active, and we need a very selective catalyst to be introduced in this DRM reaction system. Because one of the main drawbacks for the DRM is basically carbon formations problems. So by design and development of suitable and active materials to increase the efficiency of DRM, basically is the task that need to be done. This table shows how we're going to connect the CO2 mitigations with the application of DRM. So we can show you here, we have a methane can convert to the higher hydrocarbons. We have the methane to methanol. We have the methane to carbon. So by combine this is the dry reforming reaction. This is the steam reforming reactions. So by combining both reactions, it can be make a very good strategy to reduce the CO2 emission if the power is by the non-fossil fuel. However, the DRM alone basically is also a very effective method of CO2 mitigation. But the main problem is the DRM application itself will be produce many of the carbons formation in which it will deposit on the catalyst surface, and it will be cause the deactivation of the catalyst as well as will cause the reduction in the efficiency of the DRM reactions. Therefore, DRM is very depends on these new and also stable active catalysts, as well as the price of the CO2, right? To conclude, existing catalysts possess several drawbacks such as low catalytic activity and products, selectivity, accessibility and diffusion limitations, carbon deposition and metal sinterings, and also it will have a poor stability because and also the rapidly deactivations. This scheme shows you how we're going to design a very good dry reforming catalyst. So for dry reforming catalyst, basically you have a metals in which you will act as an active site and also the support. For the metal support, it will have a metal support interface. So at this metal support interface is the surface reaction mechanism occur. And that's why we need a very suitable promoter and also high metal dispersion that lead to the strong metal support interaction to enhance the DRM process. And this metal at this site basically is used to methane activations. Usually the suitable metal is nickel, cobalt, and also ruthenium. It's basically from the group of the 8 to 10 in the periodic tables. And from the supports, it's good if we have oxygen storage capacity, very high oxygen storage capacity, and also some medium strength of the basicity. It will be good to enhance the DRM process. How can nanotechnology do for these CO2 captures and also the conversions? In line with the United Nations Sustainability Development Goal 2030s, any new material or product should not be only functional and cost effective. It must also safe and sustainability, have a very high sustainability to ensure compliance with the regulation as accepted by the consumer. So we have a goal 13 over here, climate actions, means take urgent action to combat climate change and its impacts. Among the key initiatives that be taken by the Malaysian governments to against this global warming is to promote the low carbon economy. This leads me to next point, which is the nanotechnology. Nanotechnology is one of the technology that could enable such a green growth because we want the sustainable. So that's why we need the green growth. It will be less costly, more effective, and also environmentally, socially, and economically sustainable. The application of nanotechnology include the use of engineered nanomaterials, in which it will have a very unique properties. It will have a high reactivity and also high surface area, in which is very important in the CO2 captures and conversion application. Some introduction about nanomaterials. So nanomaterials are the chemical substances that having at least one dimension in the range of the nanometers. And based on ISO, it defines a nanomaterials as a material has at least one dimension in the nanoscale range of 1 to 100 nanometer. So this is the regions, the nanoscale regions of the nanomaterials. We have a type of nanomaterial. Basically, you can divide it into two types. One, we call it the natural or unintentional nanomaterials. Another one is a synthetic or artificial nanomaterials. For the natural nanomaterials, usually is produced by the nature, by the bioprocess. It's like the volcanic ash or even the virus, okay, that in our surroundings, that is the nanomaterials. But we are more concerned about synthetic artificial nanomaterials because the natural and unintentional nanomaterial, the particle size, basically will have a different size and shape and also composed of different elements. So we can't control its generations. It's not really homogeneous. However, the engineered nanoparticle, it will be more well-defined. Then it will be, usually it will be synthesized by a specific objective, and it will hold a particular interest to be applied in the various applications over here. To put it more simply, nanomaterials consist of 0 dimension, 1 dimension, 2 dimension, and 3 dimensions. And in this slide, is have list down under the 0 dimension, we have carbon ions, nanoparticles, quantum dots. If in the 3 dimension, we have pyrographene, morph, metal organic framework, as well as aerogel. Each of these nanomaterial, they have their own limitation and also advantages. It depends on what application that you want to apply. We have also different kinds of the nanomaterials in a different organization. For example, we have a nanoparticle, nanocubes, nanorods, nanosheets, and also nanodot. Two main approach used to synthesize the nanomaterials. One is called the top-down approach. Another is bottom-up approach. If top-down approach is the size of larger molecule made smaller to nanoscale. So if from the bulk materials, we reduce it to the nanoparticle. Its bottom-up approach is from the very small molecular and atomic levels, then we combine it to produce a nanomaterials. For top-down approach, we have a mechanical milling, we have etching, we have laser ablations, we have sputtering, and we have electro explosions. For on the hand, for the bottom-up approach, we have supercritical fluid synthesis, we have spinning, Schrödinger process, laser pyrolysis, chemical vapor deposition, CVD, molecular condensation, chemical reduction, and also green synthesis. I would like to introduce to you some of these syntheses. So you may see over here in this slide, this is the mechanical milling. So mechanical milling is basically a cost-effective methods for producing the materials at the nanoscale level from the bulk materials. So it's basically producing a blend of different phases, and it will be useful to produce the nanocomposite. Down here, we have a sputtering. So sputtering is a process in the solid surface will be combining with the very high energy particle. So we have a very high energy particles over here in which it combining with the solid surface. the high energy particles, for example, like the plasma or the gas. And this sputtering synthesis methods is useful and efficient to produce the thin film of nanomaterials. We have also two types of the bottoms up approach. This one, the up here is the sol gel methods. It's a very well-known methods, wet chemical technique. Usually used to synthesis the nanomaterials, metal oxides. What you call the sol gel methods, because during the synthesis, it will form the sol, okay, from the precursor of the solution, then you form the sol, then at the ends, the sol will be converted to become a network of gel. That's why this method, we call it the sol gel. Down over here, we have a CVD, the chemical vapor deposition methods. This method is very useful to to synthesize the carbon-based nanomaterials. So in CVDs, a thin film, so that's why we have a thin film. So the thin film is formed on the substrate of the surface via the chemical reaction of the vapor phase. So this vapor precursor will have a substrate over at the down, then it will be formed on this substrate surface. Nanomaterials is really unique with the properties like high surface area, excellent mechanical properties, magnetism properties, high thermal and electrical conductivity, quantum effects, and it can be a very excellent support. For the carbon captures and conversions, basically, we are looking at the high surface areas and also the porosity. In material science, characterizations is very important. Okay, so in order to synthesize very novel and functional nanomaterial, we need to characterize it with various type of these characterization technique. This I listed a few, but not limited to this slide. We have like UV spectroscopy for chemical aspect. We have the X-ray photoelectron spectroscopy, XPS, for chemical and elemental composition. We have a BET, okay, nitrogen physioption for topography, basically about porosity, the surface area, pore size, pore volume. And we have also mass spectrometry, determines the molecular weight, surface properties, and also composition. We have a microscopic technique like SEM, FISEM, TEM, basically for the morphology of the particles in their shape and also size. And we have also Raman and infrareds for the functional group analysis. So the Raman and the infrared, basically they are complementary to each other. Application of nanomaterials on CO2 capsules and conversion, we can divide it into the three categories. One is nanoporous materials. Porous material with pore diameter between 1 to 100 nanometer. We have also nano-hollow, okay, hollow structure materials, bit of combination of shell and core. We have also nanocrystalline particles, which refer to the crystalline particle which are synthesized under the nano region. So this slide shows you several types of the nanoporous materials. Over here, we have zeolites, we have MOF, metal organic framework, we have carbon nanotubes, we have also mass porous silica. Many of these materials, for example, the carbons, the nanotubes, and also the silicon-based materials, they are thermally stable up to like 200 degrees C. These properties basically is very important for post-combustion CO2 captures. And over here we have zeolite. Zeolites basically is one type of these aluminosilicates material. We have aluminum, we have a silicon, they are from frameworks. So we have a SiO-Al frameworks. And zeolites basically have acidic properties, it have a basic properties. So for the CO2 captures and conversion, we are concerned about the basic properties. The basic properties of the zeolites basically is arise from these ion exchange properties in the zeolite itself, as well as their silica alumina ratios. Another factors that I would like to emphasize here is the porosity. In CO2 captures and conversion, the porosity is very important. We have also metal organic framework. So metal organic framework, we have a metal, combination of metal, and also the organics as the ligands. So for example, we will have a copper morph, cobalt morph, and so on. Morph materials is a very it attract a very good interest in CO2 capture and conversion. This is because morph we can easily twin the pore and the natures of the morphs based on the different synthesis approach. And the morph basically will have a very significantly high surface area. So it will be act as a very good absorbance. Lastly, I would like to talk about some mass porous silica. So if you have known mass porous silica, we have a few types. We have SPA 15, we have MCM 41, we have SPA 15. So as compared the zeolites, mass porous silica to zeolites and also the morph, mass porous silica have a larger pore size. Okay, it's about 2 nanometers. It's more than 2 nanometers. So for the zeolites, usually it's a microporous in structure, so it's less than 2 nanometer. So in the microporous category, is less than 2 nanometer. If we say it's a mesoporous, it will be in 2 until 50. So if macroporous, then it will be more than the 50 nanometer. Usually mesoporous silica, when we apply it in the CO2 captures and conversion, we need to modify it. We need to do some modifications, either by doing some surface modification in terms of maybe we can load the metal oxide, or we can introduce the amines, or we can also grafting it with the polymer, for example. Why is it we need to do the modification of the mass porous silica? This is because the surface of the mass porous silica basically consists of the very mildly acidic silanol group, the SiOH. So this is not really good for the CO2 capture. The CO2 itself is very mild acidic, so it will be attract to the absorbent that it will have basic properties. This is why we need to modify the mass porous silica to enhance the basic property itself, as well as to enhance the CO2 absorption performance. This slide is to show you a few types of these nano hollow structures. Hollow means that there is the empty in the middle, right? So it's like core shell structures. So the special of these non-hollow structure materials, basically we have abundance of accessible active site. Okay, so the active site is needed to use for CO2 captures applications. We can also do some modification for the hollow nanomaterials, functionalizations. We can do the geometry and composition modifications. Can make it in terms of the multi-cell, and we can also do surface molecular engineering, the modification of the surface, and make it to become a single atomic. Also, we can encapsulate it with the others materials. Here, I would like to show you that there is a few, some of these nanomaterial that being applied for the CO2 captures and conversions. For example, we have a carbon nanotube over here, we have graphene, we have a fluorine. So 3 of them basically is the carbon-based nanomaterials. Then people are also interested to apply the metal oxide nanoparticles in the CO2 capture and conversions. Okay, we have also dendrimers, hyperbranch polymers, and also the GIF, zeolite inorganic framework. So this is one type of these morph. Next, I would like to proceed to some of my current research. So our current research basically focus on few materials, mesperolite ZSM5, mesperosilica. Then I will some of the fibrous material, fibrous silica and fibrojolite ZSM5. And some of my students will do some about core shell materials and also metal organic frameworks. We have studied the CO2 captures and also CO2 conversion by using several types of the materials as listed in these slides. Basically, recently we are using the fibrous materials. I would like to share with you some of my recent publications. So this is the applications of the fibrous silica materials with various type modified with various type of metal oxides for CO2 capturing. So by loading with the metal oxide, we may see that there is the disappearance of the dendrimeric. This we call it the dendrimeric structures. So there is the disappearance of the dendrimeric structures of our samples. We try to compare it with different types of the metal oxide like calcium oxide, magnesium oxide, and also the styrene oxide. And based on the studies, calcium oxide shows the calcium oxide fibrous silica material show the best for the physisorptions CO2. So basically in the CO2, we have two types of the absorption. One, we call it the CO2 physisorption. Another one is the CO2 chemisorptions. The difference between both of them, physisorption is so it will be due to the van der Waals forces and it will be multi-layers. While the CO2 chemisorptions, basically it will have a bonding. If you have a bonding, then it will be needed a much very high energy. We also did the stability test run for 5 cycles for our calcium oxide fibrous silica materials, and it shows that it's quite stable for up to 5 cycles. The good performance of these CO2 absorptions in the calcium oxide fibrous silica, we can say is that this is due to the basicity, basicity properties, and also the porosities that arise from the fibrous morphologies. And we can conclude that the CO2 physisorption is basically depends on the porosity and also the basic strength, while the CO2 chemisorption is depend on the basic strength and also the basic size that present on our absorbents. We also studies on this effect of the copper oxide loading on the fibrous HSM5 jolite for the carbon dioxide captures. And these fibrous morphologies of this fiber HSM5 is very important because it offers a very high surface area and porosity in which it will enhance the CO2 absorption performance. So these all types of the absorbent, we call it the physical solid absorbent. So this physical solid absorbent is exhibit excellent CO2 absorption desorption capacity, good stabilities, and high reusability. So this metal oxide, it provides a suitable basicity because as I mentioned earlier, the CO2 is basically a mild acidic. So this metal oxide can form a chemical bonding with the CO2. And it have a high CO2 affinity. It will be offering more absorption site for CO2 absorptions, while the fibrous material is act as the support of our materials. So because fiber material have a large surface area, abundance of porosity, stable framework, easy to be tailored, and also unique morphologies. I believe that by combining both metal oxide and also fibrous material, it can be develop a very efficient and also sustainable absorbents. We also studies, we also synthesize the fibrous SPA15. So this fibrous SPA15s, we study on the CO2 methanation. So in these slides, we propose the possible mechanism for this nickel fibrous SPA15 as compared to the nickel SPA15. If in the nickel fibrous SPA15, we have three types of the intermediate species. We have a bidentate carbonate, we have a unidentate carbonates, and we have a linear carbonate. So this is the bidentate carbonates. Okay, so this is the unidentates. Then we have a linear carbonate. And while for the nickel SPA15, there is only we only observe the bidentate carbonate that present as the intermediate species. This mechanism, basically, we are using this in situ FDRR to study the whole process. In the reactions for the CO2 methanation, we can say that the nickel fibrous SPA15s process a very good activities. So it achieved about 99.7% of the CO2 conversion and also 98.2% of the methane yield. Because the CO2 methanation basically is CO2 convert to methane. So we have a very high CO2 conversion. So we compare of nickel fiber SPA15 with the nickel SPA15. And it also shows that the nickel fiber SPA15 is very stable up to 180 hours. We also did explore about different hydrothermal treatment techniques. For example, we have a reflux hydrothermal, Teflon hydrothermals, and also the W is the without hydrothermals. In this study, we have carried out different kinds of these characterizations. We have carried out the XRD, we have nitrogen physioption. We have also determines the basicity properties by using the FDRR pyros. So if you didn't know what is FDR pyros, basically if there will be a peak at 3467 over here, in which it shows a very the basic peaks of our samples. Highest peaks of the higher intensity of the peak at 3467, it will be have exhibit a very high basicity. And this is when we compare the three techniques. So it shows that the reflux, the R, it shows a very high CO2 conversions. And also the CH4 yields as compared to others technique. This is due to the very high surface areas, the smaller metal particle size, and also strong metal support interactions of this reflux by using these reflux techniques. We also carry out studies on the CO2 reforming of methanes. We are using the nickel Syria SPA15. So this nickel Syria SPA15, we are in this study, we carry out by using different types of methods, like the conventional impregnation, ultrasonic impregnations, and also reflux impregnations. So then we carry out the different kinds of the characterization methods. Then in the end of this CO2 dry reforming, it shows that the ultrasonic methods is the best as compared to others methods. And it can be stable. So this nickel Syria SPA15 ultrasonic impregnation is this one. So for the CO2 conversion, CO2 CH4 conversions, because for the CO2 dry reformings, you will have two reactants. One is CH4, another one is CO2. So CH4 plus CO2, then it will produce the H2 plus CO. So in this case, we will have for this method, ultrasonic impregnation method, we have a very high CH4 conversion, we have a high CO2 conversion, and we produce about H2 to CO ratio about 1. And it can be sustained to 48 hours. I would like to draw your attention on our current review papers that is published about the nanosilica materials for syngas productions via CO2 reforming of methane. So we highlight that the nanosilica supports are preferred due to their high thermal stability and porosity. Then we have different types of nanosilica support that have been discussed in this review paper. For example, we have mesoporous, we have dendritic fibrous, and also core shell. And dendritic fibrous nanosilica have high accessible active site. So they will be lead to minor clocking of the materials. And while the core cell nanosilica will have a very low internal diffusion resistance and also confinement effect. For dry reformings of methane, basically it will be very important for coke management. So this can be managed by the basic natures and also oxygen storage capacity of the support. This slide I would like to just show you, get some ideas on how is it the Stoja methods to synthesis the mesoporous nanosilica and also to synthesis the dendritic fibrous nanosilica. So in this slide, the nanosilica, dendritic fibrous nanosilica is synthesized by using the microemulsion technique. So the Stojal, so we have a CTAB as a template, right? Then at the ends, we will remove the templates. The trios is basically the silica precursor, okay, to produce the nanosilica. General roles of each catalytic quantity in the nanosilica. So for the DRM, basically we need a metal and also catalyst supports. So we need to concerns about the active metal dispersions, as well as the crystalline size, acidity and basicity, oxygen mobility, surface areas, and also the morphologies of the materials. These all catalytic properties is needed to give a very good nanosilica catalyst properties in order to boost the CO2 reforming process. Lastly is about the Syria. So I would like to talk about some Syria catalysts. So Syria is very unique because it can act as a supports and it can act as a active metals. And recently is also a lot of these concerns about the use of the Syria's materials for dry reforming of methane. The very important properties in Syria is that it has a redox and acid-base properties and also a very high oxygen storage properties, in which it will be greatly affect the catalytic behavior of the materials, as well as it will be very important for coke inhibitions in the DRM process. So this slide is some would like to wrap up. This slide shows the CO2 captures using selective porous absorbance materials, and we can be convert it into various type of products, like for chemicals by chemical conversions to achieve a very sustainable economy. And I believe that by using the nanotechnology, it can provide a very viable material solutions to these complex technological problems. Because the field of the nanotechnologies can offer several advantages over a very traditional approach. For example, in the conversion of the carbon dioxide to more useful materials, because nanomaterial have a very unique properties, a very great degree of the high surface area and also porosity. So for the CO2 capture, is really the important one is the porosity. So, and also this will be result in the more interaction of the absorbent with the CO2 and also the active site, and it will be increased absorptions and as well as the kinetic of the CO2 absorptions. And by this, it will be enhance the DRM, CO2 mination, and also CO2 absorptions. Last but not least, our focus basically is on the design and synthesis of material, characterization of material, and also CO2 capture and CO2 conversion applications. I will be feel free if you are interested to collaborate in any kind of these projects. That's bring me to the end of my presentation today. I would like to acknowledge the Ministry of Higher Education Malaysia and also University Kebangsaan Malaysia for their grant finding. Local and international collaborator for their assistance and support, and also my former and present undergraduate and postgraduate students for their hard work and commitment in carry out all the experiment and also write all the papers. Okay, that's all from me, and thank you. Terima kasih.
Okay. Thank you very much, Dr. Pang, for the insightful lecture about the material for the carbon dioxide capture and conversion. So I would like to open the floor for the question and answer session. If there is anyone want to ask question, please feel free. And if anyone has some trouble with the maybe internet connection, you can ask by typing in the chat section. Okay, so if there's anyone, please. Oh, first, and if there is having a difficulty delivering it in English, maybe you can chat me and then I'll deliver to Dr. Pang. Okay. Pang, Dr. Pang, I have a question from a student. They ask, what is the use of syngas, the CO2, CO and hydrogen from the DRM process?
Syngas basically used as energy. So it's like we can energy storage as well as can be converted to others chemicals.
Ah, okay. So it's used as a means of energy storage.
Yes, energy storage. Mainly it's energy storage
Okay.
or fuels.
Okay. One question is this is from another student. Before you present the Sabatier and the Fischer-Tropsch reaction, uh, what is the main difference between the two process? Because viewing from the equation, it's pretty much similar.
Uh, the difference between the Sabatiers, I think I just show, right? This one.
Yeah.
A Sabatier reaction is basically to produce the methanes, while the Fischer-Tropsch, it can produce the methanes and also other types of hydrocarbons. While Sabatier is only for methanes. And so the difference, the huge difference, I think, is the Sabatier reaction we can carry out in terms of ATM, so atmospheric pressure, while the Fischer-Tropsch usually need very high pressures. That's why Sabatier reaction is more preferred as compared to the Fischer-Tropsch reactions.
Okay.
In the technical wise.
So Fischer-Tropsch reaction require much more harsh condition compared to the Sabatier reaction.
Yes.
And maybe require a different set of catalysts to accommodate it in the milder environment.
Sabatier reactions, basically we can conduct it in the very low temperatures, less than 500. You should somehow like sometimes people can carry out about 200 to 300. While the Fischer-Tropsch and also at 1 atm, the Sabatier at 1 atm means the atmospheric pressures. So the Fischer-Tropsch it needs about very high in terms of the pressure. That's why we need to design and also develop the catalyst that suits the conditions of the Fischer-Tropsch.
Okay. Okay. Thank you very much, Dr. Pang, for the question for the answer. And there is, if you can open the chat, there is a question from Mr. Tahta Amril.
What's okay? Tata.
Yes.
Okay. What is the main difference between N2 conversions to NH3 with CO2 to methane, and what requirement we should have to convert N2 into NH3? Nitrogen conversion to NH3, you means the Haber reactions?
It's like
Yes.
yeah, photocatalyst or electrocatalyst to convert N2 into ammonia, something like that. Is it the mechanism is similar with yours or different? Actually, I'm interested to study this one.
Oh, okay. Okay, because I never go through with this N2 conversion to ammonia, but I don't think they are similar because N2 is inert, right? So I think you need a very different kinds of these materials to convert the N2 to ammonia. Because for the CO2, we know there is a mild acidity. That's why when we in designing the absorbents, we can tailor the properties to become more basic in order we have a more CO2 absorb on our absorbent. But for the N2, I think there is a different case. Maybe we can discuss in detail later on, but I don't have any idea on this one at the moment.
I see. Thank you.
But there is a very interesting questions. N2 conversion to ammonia. Thanks, Tata. Right?
Okay, thank you.
Okay. Is there any other question? I have some question from the other student, so I'll deliver it to you. So, one of the student asked that, can the material also works as a temporary means for carbon dioxide storage? So not converting it, maybe like just keep the carbon dioxide
Okay.
there.
Oh, means okay. Yes, because basically, nowadays we are tends to use like one material. It can be have dual functions. Means that it can capture the CO2 and also it can convert. But yes, it can be like you only focus on the CO2 capture, like storage only, but not converting it. Because if let's say for example, if you want to capture the CO2, means you need to tailor the properties of the material, the absorbance we call it, in terms of porosity. We are very concerned about porosity and also the basicity. But for the CO2 conversion, we need to have two components. One is the metal, another is the support. So this metal that introduced onto these supports must be very active. For example, we have to use the nickel, we have to use the cobalt, we have to use the ruthenium, any noble catalyst active to active the CH4 activation. But this this metal active site may not need on this CO2 capture, only in the CO2 conversion. So
Okay.
in the CO2 capture, basically, we can tailor it by introduce the base, we can say base elements like the metal oxide, the base metal oxide, or like amine. But for the CO2 conversion, we are concerned about the metal active site, not really about the basicity itself only.
Okay. On this topic, so if we already capture, like we have a material that contain a captured carbon dioxide, can we process it later? Like maybe we store it and then later we process the carbon dioxide to convert it into something like that.
At the moment, we haven't do like this. Because for the CO2 capture process, basically is only to capture the CO2. Then we can, it's like CCS, it's carbon capture and storage system. It's only keep it. But it's haven't go to like the technology now haven't go to like we keep it, then later you take it out, then we do for the CO2 conversions.
Oh, okay. So
Maybe in the future, but not now.
so it hasn't converging yet between the
Yes,
CCS and the carbon and storage and conversion.
yes, correct.
Okay. Ah, I have there's one other question. What is the benefit of material with larger pore than that of the carbon dioxide? Like I think the slide you show has carbon dioxide around 0.12 nanometer.
Mm.
I and yeah, what is
Ah,
the benefit? Like if it's larger, maybe it can easily pass through and not captured like that.
mm, so the CO2 captures basically, if we say it will have the high efficiency, then it's microporous. So if we compare the mesoporous, and also the macroporous, then the macroporous definitely will give a very high CO2 physioptions. But the larger pore of the material is maybe used in terms of we do some modifications to enhance the performance of the CO2 absorptions. So if you talk about the physioptions, a CO2 physioption, it must be like give a very high performance. It will be microporous material. But if let's say you want to modify it, then we tend to use a larger pore like meso or macro for modifications, because we would like to introduce other components onto the system. Because if let's say you use the microporous, then it will tend to clog all the pore size of these microporous material, right? So we don't have any pore for the CO2 capture later on.
Okay. Thank you very much for the answer, Dr. Pang. If there's anyone wants to ask question, you can freely speak to the use the microphone.
Can I ask a question?
Okay.
Yes.
Okay. Okay. Thank you so much, Dr. Peng. So I'm Prastika. I'm in the same department, lecturer with Dr. Lutfi. Okay. So thank you very much for your presentations. Actually, I'm working a lot from my master until PhD to work with CO2 reductions. So I think it has a correlations also with your work about the CO2 absorption. I ever work with CO2 absorption with amine solutions, as you mentioned before, the CCS, right? With the MEA. Yeah, MEA solutions. Yes, amine solutions. And then I moved to the carbonate solutions because it's more easier actually. Until now, I'm still working with that for electrochemical reductions applications. And sometimes we still has a difficulty how we promote the CO2 itself close to the electrode. So listening to your presentations, you use kind of some materials like maybe ceria or MOFs or zeolite to absorb the CO2 into that materials. And then I'm thinking, how about if we modify that materials to some electrodes and then use that for CO2 reduction? Is that possible? Or what do you think about that actually? To take the CO2 from the solutions close to the surface of the electrode. I think, is there some possibility for that? Yeah. Thank you.
Okay, thanks, Dr. Prastika, right? If I pronounce it correct. Yes, I think it's possible because actually I have a project about this CO2 reductions with the India. Yeah, because it's if you say about CO2 reduction, basically we are dealing with about the electrochemical property. Yeah, I think it's possible if let's say you want to coat the powders onto your electrodes. I mean the active one, then I think it's possible to convert it to the to capture the CO2 and also to reduce it. I think we can talk about it later on.
Yeah, sure. Yeah. Like one more questions. If we use kind of MEA solutions like amine solutions, the CO2 will become the carbonate, right? The CO3 minus or HCO3 minus. how about if we absorb in kind of the materials you synthesize? Is it in the form of CO2 or something else, like already changing to the ionic form or something else?
Okay, because if like, is it possible, like, I think like if I have a solid absorbent, because basically I'm dealing with the solid absorbent. So this solid absorbent, I think it can be like reloading some of the MEA or something like that, or right? So this, we can loading some low amount of the MEA onto the solid absorbents. So then there will be still the interaction. I think it will be the chemisorption interactions.
Yes.
Right? So it will be have a chemisorption interactions with the CO2. But I concern here is that maybe we need a very large surface area of the absorbents. I mean the supports.
Yes.
Well, previously I'm dealing with this amine too, but yeah, it's got it's not really easy to be controlled.
Right.
And
It's
it
changing
only,
a lot, right?
it stays very low. What we call it? It only happens at low temperatures.
Yeah.
Yeah, it's very easy to be boiled and something. So about, I mean, we have to concern about that. So, but I think if let's say reloading it onto a very stable solid absorbent, so it will be enhance the thermal stability of the whole system.
Yeah, because when we work with that with MEA solution, it's really difficult because it's changing a lot, and then when we do characterizations, it's very difficult to find the products, yeah, something like that, and then we just move to a simple amine solution, kind of ammonia, something like that. Finally, yeah. So also you make a solid materials, right? So not kind of a membrane in the solutions, not like that.
No, just just solid absorbent. So but now I'm lastly maybe I can introduce you with the fibrous materials, because fibrous material I think is very good in terms of surface area, and also the moth materials.
Even the cereal also solid.
Cerium also but cereal will have a very low surface area as compared to the fibrous material. Although it's good, right? Because if, let's say you want to load your MEA, it is like even give not really good effect.
I see. Okay, thank you so much, Dr. Peng.
We can discuss about that.
Yeah, sure. Yeah, thank you. Okay, thank you, Dr. Lutfi.
Thank you.
Yeah, thank you.
Okay, is there any other question? If there's not, if there's there isn't, I have my question from my own regarding your research in the fibrous SBA 15. So according to the reaction schematic, the reaction proposal, the reaction occur in the oxygen site of the SBA 15. And then, so what is the purpose of the nickel in the material?
Nickel is basically to dissociate the methane, because in the CO2 dry reforming, basically we have two reactants. One is the CH4, another one is the CO2. So the CH4, it will be absorbed on this metal active site, then it will be dissociated. So because we need the H, right? The H of this methane. So then it will be spilled over onto this support. Then the CO2 basically will be absorbed on the support. There will be interactions on that, to form the carbonate and so on. Then it will be converted to become the syngas later on.
Okay. And according to the reaction process, the synthesis procedure, did you impregnate the SBA 15 with nickel during the synthesis or post-synthesis?
Post-synthesis. Because we would like to control it on the surface. If like we do it like one pot, then it will be anywhere, right?
Yeah.
Yes. So basically it's a post-impregnations after we already synthesized the fibrous SBA 15.
Okay. So how about the loading capacity of the fibrous SBA 15 and the SBA 15?
You mean the loading of these nickel?
Yes, the loading of the nickel and the absorption capacity towards the both precursor, carbon dioxide and methane?
For now, because we only need a very low amount of the metal active site. So usually we only impregnate about 5%, maybe lower than that. Because it's more than that, then it will be clog all the surface, right? So we tend to get it like as low as possible. But for our case in our study, we impregnate it with the 5%.
And
So,
how about the capacity, absorption capacity?
If let's say you look, because nickel actually is quite active, then we combine it with the fibrous SPA 15, then the conversions is about 90% over. So it means the CO2 conversion and also the methane conversions.
Oh, okay. Okay, thank you very much, Dr. Pang, for the answer. I have an announcement for the participant to fill out the the form for the participation form for the lecture. I've already posted the link in the chat, and I'll post it again in case anyone missed it. Okay, so is there any other question? Okay, so I think there is no more question from the participant. Thank you very much, Dr. Pang, for the lecture. And do you have any one or two words for the student and maybe for the staff?
Okay. Thank you for participates for the today lectures. Thank you for the Dr. Luffy, and also I just know Dr. Prastika for the present of today. And I hope that this is not the beginning, this is not the end, but the beginnings of all. So the CO2 basically is climate issues. Then I hope that at the end of my lecture, you get some brief ideas of what is the materials, what is the CO2, and what is the CO2 conversions. All right, and thank you all, and terima kasih.
Okay, thank you very much, Dr. Pang, for the lecture.
Thank you so much, Dr. Peng.
Hopefully, later we can do collaboration between Universitas Airlangga and the University Kebangsaan Malaysia.
Sure. You can discuss about it later on.
Dr. Prastika and Dr. Pang can collaborate.
We need to make it in the future. Yeah, sure.
Yeah. Okay. Thank you very much, Dr. Pang, and good afternoon, everyone.
Thank
And
you.
have a good day. Stay safe.
Yes, you too. Stay safe.
Okay. I'll end the lecture now. Thank you very much, everyone.